European Roadmap towards Fusion Electricity. Number 3. Developing plasma regime of operation for ITER and DEMO. Achieving power from fusion requires the confinement of a high-performance plasma at high enough density and temperature for a long enough time. However, at the same time, any instabilities and transport processes that might arise in the plasma must be controlled. The power loads on the plasma facing components, which must be very thin in demo as the neutrons need to lose their energy in the bleeding blanket, and in the diverter must be acceptable for demo. This implies typical wall loads less than 1 million watt per meter square on the wall and less than 10 megawatt per meter square on the diverter. To make these possible, highly radiative plasmas must be engineered where most of the radiation is uniformly emitted from the plasma edge. Carbon has been for a long time the standard material for the plasma-facing component, as it is rather forgiving when the plasma touches the wall. Unfortunately, carbon reacts easily with hydrogenic isotopes, including tritium, to form carbon hydrate. Additionally, carbon easily forms dust, with the result that much of the tritium would lay on the bottom of the tokamak. Therefore, in Europe, a clear decision was made towards metallic plasma-facing component. This was first pioneered on ASDEX upgrade, which was gradually equipped with a tungsten wall and later followed by jet, where most of the wall was changed to beryllium, while the diverter was changed to tungsten. As a result, the tritium retention dropped by a factor of 20 to a level low enough for ITER to be able to work for a long time without any opening to get the tritium out. A drawback of the metallic wall, however, is the fact that it is less straightforward to make high-performance plasma, as the heavy metals from the diverter have a tendency to migrate into the core plasma. Special operational procedures are needed to achieve high-performance operation in a metal wall tokamak. This involves ample central heating, seeding of the edge plasma with noble gases, flushing impurities, with beginning edge localized models, etc. Detailed studies at JET over a number of years were needed to bring the performance with the ITER-like wall back to the same level as with the former carbon wall. The effect of choking of the plasma performance due to influx of heavy metal impurities is in general less severe in a large tokamak with a large volume to surface ratio. The operation at high performance near the operational limits comes at a price, namely disruptions, in which the plasma comes to a sudden termination lead to strong forces on the vacuum vessel. These become stronger for larger devices, and therefore much effort needs to be devoted to avoiding surprising and/or mitigating disruptions by using such techniques as massive gas and shattered pellet injection. Much effort is devoted to predict well in time whether a disruption has a likelihood to occur during the plasma discharge, such that measures can still be taken to avoid the disruption.